Next one is physical properties of haloalkanes and haloarenes. Clear? First one, pure alkyl halides are colorless, but bromides and iodides develop color when exposed to light. Okay? And next one, melting and boiling points. You know, if you compare the melting points of alkyl halides and alkanes of comparable masses, alkyl halides have high boiling points than the alkanes of comparable masses. Clear? Alkyl halides have high boiling points than the alkanes of comparable masses. Why this is? Why alkyl halides are high boiling points than the alkanes of comparable masses? You know, alkyl halides are polar molecules. These are polar because you know, and here halogen is more electronegative than the carbon, so that's why halogen acquires positive charge, negative charge, and carbon acquires positive charge. So that's why you know electronegativity difference is there between the carbon and halogen atom. So that's why the molecule is polar. We have already discussed. But here RH, hydrogen and carbon electronegativity difference is very small, almost equal. So that's why these are non-polar molecules. These are non-polar. Clear? If polar molecules are there, then two types of intermolecular forces are existed. One is dipole-dipole interactions, and the second one is van der Waals interactions. But if non-polar molecules, there is only one type of intermolecular attraction forces present. That one is van der Waals attractions. So that's why here two types of attractions present among the alkyl halides. So, and boiling points of alkyl halides are higher than the alkanes of comparable masses. Clear? Greater the attractions and higher will be the boiling points. You have to break all the bonds. You have to supply more amount of the heat energy. So that's why alkyl halides are high boiling points than the alkanes. Clear? Now, if I take suppose in this one, among the alkyl halides, which one have high boiling? Which one has high boiling point? Suppose I will write. I will not change here. I will take the alkyl group is same. I will write here alkyl iodides, alkyl bromide, alkyl chloride, and alkyl fluoride. So among these, which one has high boiling point? Which one has high boiling point? You know that boiling points always directly proportional to attraction forces. That is mainly van der Waals attraction forces. Okay? These van der Waals attraction forces depends upon, you know, surface area. This is depend upon which one here? Surface area. Greater the surface area and van der Waals attractions are higher, then automatically boiling points also increases. So that's why it depends upon the surface area. Now you see in this one, all alkyl groups are same, but here halogen atom is different. Iodine, and here bromine, chlorine, and fluorine. You know that as you move down in the group, size increases. So that's why iodide is and bigger size than compared to the bromine, chlorine, and iodine. If size this molecule size is greater compared to the remaining all molecules, so that's why size greater automatically, and it has the high surface, larger surface area, then having high van der Waals forces, so that's why it will have high boiling points. So what will be the R of the boiling points here? And it depends upon the size of halogen atom. Greater the size and greater will be the van der Waals forces, automatically boiling points also increases. Clear? So this is the first one. And the second one, I will take now here halogen atom is same and I will change the alkyl group. Suppose I will write here CH3X and CH3CH2X. Next one CH3CH2 CH2X, and the next one is CH3CH2CH2CH2X. Any halogen atom you can take. Clear? But all halogen atom is same, but alkyl group is different. Clear? In this case, what will be the boiling points? What is the order of boiling points of these molecules we have to discuss. Clear? Now you know that here, and as the molecular mass increases, boiling points also increases. Clear? You know that. Here, this is as the chain length increases, surface area increases. Chain length increases, what happened here? Surface area increases. Surface area increases, van der Waals force of attractions increases, then automatically boiling points also increases. So that's why what will be the order here? And this molecule will have great high boiling points compared to the remaining. So if you take these two, and this one will have the large surface area compared to this molecule. So that's why order of the boiling points of this 4 molecule is in this way. Then what will be the isomeric alkyl halides? Isomeric means, remember always, primary alkyl halides have high boiling points than the secondary than the tertiary. Remember, why? You see, simple, I will write one example. CH3, CH2, CH2, CH2X. Clear? Next one, I will write CH3, CH2, CH, and here, suppose bromine I will take, no problem, any halogen you take, same type of halogen atoms here, bromine, and you will get CH3, and the next one, CH3, CH3, CH3Br. These are having all these 3 molecules having the same molecular formula, but the structures are different. Now, what is the boiling point order in these 3 molecules? Clear? You know that as the surface area increases, van der Waals force of attraction increases, boiling points also increases. Clear? In this case, you see, if you take this molecule, you see, as branching increases, surface area decreases. See now, here surface area and here surface area. Clear? As the branching increases, these are branches increases, surface area decreases. As the surface area decreases, van der Waals forces of attractions decreases, then boiling points also decreases. So that's why you know that this is the order of boiling point. So that's why primary alkyl halides always will have high boiling points than the secondary than the tertiary. Clear? And next one, fourth one, as the number of halogen atoms increases, automatically molecular mass increases, then surface area also increases, and van der Waals forces increases, boiling points also increases. Clear? Means as the number of halogen atoms increases, boiling point also increases. Take the example. Suppose I will take the CH3Br here. Next one CH2Br2. Next one CHBr3, and next one CBr4. So which one has high boiling point here? So this is, you know that as the number of halogen atoms increases, and the boiling points here, boiling point is directly proportional to number of halogen atoms. It depends upon same here only. As the number of halogen atoms increases, you know, surface area increases, then van der Waals forces of attraction increases, boiling point also increases. This is the melting. And same, melting and boiling points are directly proportional to van der Waals forces, and van der Waals forces is directly proportional to surface area. So next one is boiling points of isomeric dihalogens are very nearly the same. If you compare boiling points of dihalobenzenes like ortho-dichlorobenzene, para-dichlorobenzene and meta-dichlorobenzene, and boiling point difference means almost same, slightly differ but almost same. So which one will have the highest boiling point means ortho, and after then para, then meta. If you compare here polarity order, if you compare, what is the polarity order? You already know the polarity order of the compound is ortho, and after then this is polarity order, means dipole moment I am saying, dipole moment order. So dipole moment order meta, and after then what it is? Pair. This is the dipole moment order, means polarity order. If you see like this, means ortho dichlorobenzene should have high boiling points than the meta dichloro should have high boiling point than the para dichloro, but you see para dichlorobenzene comes before the meta dichloro. Why? Means you have to consider not only the dipole moment here, you have to consider the resonance effect and the inductive effect here, and by that you have to, by seeing the resonance effect and inductive effect, you have to see the polarity of the molecule. So then if you see like this, this will be the order. Clear? The next one, melting point order is para greater than ortho greater than meta. Why? Means the melting point depends upon the packing of the molecule. If the molecules are tightly packed, then we have to supply, so means we have to supply a high amount of, means more amount of heat energy to break that. Means automatically melting points increases. I am talking about the crystal. Crystal means solid. Solid means melting point. Clear? So that's why if packing is perfect, then automatically that compound will have high melting points. Clear? So that's why if you see the packing order, this is, you know what it is, para dichlorobenzene, symmetric molecule. If molecule is symmetrical, then packing will be very tight. If packing is tight, then automatically melting points will increase. So what is the packing order of this molecule in the crystal lattice is para, ortho and meta. Clear? So in the NCERT, means in the PU examination, sometimes they are asking why para dichlorobenzene has high melting point than the ortho and meta dichlorobenzene. What is the answer? It is due to, you know, I already mentioned, it is a which molecule? Symmetrical molecule. Due to the symmetry of the para isomer that fits in the crystal lattice better compared to the ortho and meta isomer. I already said if molecule is symmetric and it will fit better in the crystal lattice. Clear? That is the answer. Next one, density. If you see, you know, bromo and iodo derivatives of hydrocarbons are heavier than water, and fluoro and chloro derivatives of hydrocarbons are lighter than water, because you know, as the size increases, molecular mass also increases, and then automatically density increases. See, if you take alkyl halides, what is the density order? You know, I already said here alkyl groups are same. Which one is different here? Halogens. As you know, iodide molecular mass will be greater than the bromide, chloride and chlorine and fluorine. So that's why as the mass increases, density increases. So the order of the density of the alkyl halides is in this way. Next one, solubility. Alkyl halides are slightly soluble in water but highly soluble in organic solvents. Why these are slightly soluble in water? Means they cannot form strong hydrogen bonds with the water molecules. Clear? They cannot form strong hydrogen bonds with the water molecules. So that's why the solubility of these molecules in the water is very less. This is the reason why they are slightly soluble. Haloalkanes cannot form strong hydrogen bond with the water molecule, so that's why they are less soluble in water.